All right, back with example 2. The population of Drefton is 4,000 but doubles every 32 years. How long until the population reaches 10,000? Well, this is one of those doubling time question, right? There's the key word, doubles. And so I'm going to write that formula down and see if we can't figure out what these variables are supposed to mean. We should be able if we got 4 variables, we should be able to figure out 3 of them and then solve for the last one. A is the amount at the end. Well, what's the population at the end of all this? Well, it's 10,000. The amount at the start, the population is 4,000. T it doubles every 32 years. That's the doubling time, and we want to know how long until it grows from being a town of 4,000 to a city of 10,000. And I'm actually going to use the second technique, which is the graphing calculator TI-83 graphs. But before I do, let's just think about this. Now, this is time and this is population or amount. Now it's 4,000. Notice in 32 years, it's going to be doubled. It's going to be 8,000. Another 32 years, 64 from now, it'll be twice that. It'll be 16,000. And so on. If I wanted to keep going, I could. But I want to know when the population will be 10,000. Well, it's in here somewhere, right? So it's somewhere between 32 and 64, but the question is where. If I were using the other technique, the guess and check technique, I might try 40 years, I might try 45 years and guess and check. What I'm going to do is use the graphing calculator. Now when you turn it on, it might be in all sorts of state. Follow the instructions from yesterday's or last day's lesson, or the instructions from your textbook. The technique. Oh yeah, hang on. I gotta still substitute in, because what am I going to put in the y equals? Well, a is 10,000. Little a, the initial amount was 4,000. My base is 2. My exponent is t over 32. And I know the answer is going to be somewhere between 32 and 64, but how I use I'm going to graph the left side, and I'm going to graph the right side and see where they cross. So I'm going to put that one in the left side, 2 to the exponent, and now notice I got to put brackets around this, just like if you put it in your graphing your scientific calculator. If you're a guess and check person, that's got to go into brackets. And this is the unknown button. It comes up as an X, but that's all good. Divided by 32. And then the other side is going to be 10,000. Oops, not 11,000, 10,000. 10,000. And before I hit graph, because it could be all sorts of crazy settings, I got to set my window settings. And I don't know about the years, except for I kind of thought about it, and I know it's going to go up to almost 64 years. So maybe I'll put in 60 years here. And I know that as far as the outputs, the output has to get up to 10,000. So I'm going to put in a number that's higher than 10,000 so I can see where my graph gets crossed. That's 120. There's 12,000. Each tick I'm going to say is worth 1,000. Right? Okay, and then if I press graph, hopefully there's no errors. There's my exponential growth, slow and steady growth in Drefton. And there's the 10,000 mark, and that's my intersection point. Remember, one of the ways was to press trace and then go over and find it, but we found that a little bit clumsy. Didn't quite get right there. So the fast way to do it is using the second trace, the calc menu, and then I go to intersect, put in the 2 curves that I want, and then I get close to the intersection as a guess and press enter. Doesn't matter how close I get, and then it tells me. So as far as your solution, copy that graph, say that you use the TI-83 graph, and I'm going to sort of sketch it. it looked like this. Like that. And that point there was, what was it? 42.3 and 10,000. And that matches what we said logically. The city will reach 10,000 people in 42.3 years. Okay, next. Last example of the whole unit. Isn't this exciting? There's actually a background video. Carbon dating is a very interesting application of half-life, of exponential decay half-life. And so in the calendar, there's a background video, and it's got to do with carbon dating. It's the idea of using radioactive decay to figure out how old stuff is. So the half-life is this, and a relic was measured to have 35 milligrams of C14. And what's C14? Well, watch the video and you get the background for it. Well, it should have 100 milligrams before it started decaying. So write the model for this situation. Well, this was it. Or the fraction of half, doesn't matter. A equals whatever, and we're going to have to figure these out. T equals and H equals. A was the amount at the end is after it decayed, right? It's the smaller number is the amount at the end because it's decaying. Started at 100, ended up with 35. How old is the relic is what we're going to want to find. That's what we're finding down here for B. H is the half-life. That's a long time, right? These radioactive elements have a long time to decay, 5,700 years. Okay, write the model for this situation. Well, the amount at the end, I'm going to write it like this. 35 equals 100, 0.5 T over 5730. And that's all in the exponent. That's kind of hard for me to write, but that's all in the exponent. How old is the relic? Well, we've got to solve this exponential equation. We can do it any of the ways. We could do it guess and check. We could use the graph. I'm going to use the third way, which is the calculator and the table. So how we do that is we still got to clear all this other crud out. We still got to put the equation into the y equals part. So I'm going to put the right hand side here, 100. Why it does that, I got no idea. I'm going to go up to 100 times 0.5. I should maybe put a bracket in there, maybe a 0.5 to the exponent bracket x divided by 5730 bracket. And then to use the table, remember I used the table setup. Second window was to set up the table. And we're starting at 0 and going up by 1 years. Well, that would be a long time, because if we think about this logically, it's going to be a long time, right? Because here, I'm going to think about this logically over here on the side. So at the start, it was 100 milligrams, right? Then 5,700 years, it would be half as much. Another 5,700 years, which, what would that be? That'd be like 11,460 or something, like another one, another doubling time, not half-life, another half-life away. That would be 25. So it's going to be a long time, right? This is going to be like somewhere in here somewhere, 7,000 years or something. And so if we went up by ones, that wouldn't be very good. But remember, when we select ask there, then that allows us to input whatever we want into the table. So I press not graph, but second graph to get to the table. And see, it's got all the crud from the last example in there, but I'm just going to start pounding away my own guesses here, and it'll just overwrite what we had in there. So, for instance, what would be a good guess? Well, I said that 5,000 years was going to be about half, but I'm looking for this value to be 35, right? So let's go around 8,000. Well, now we're getting closer. It's still got to decay more, though, to get to 35. So I'm going to go up. I don't think 9,000 will be a good guess. I think that'll be too low. Yeah, that's too low. I need that to be 35, so I don't need it to decay as much. I need to go back 8,500 years. See, now we're getting close, right? I want to get it so if I round this, it's 35. It needs to decay more, so I need to go up a little bit from 8,500 years. Still needs to decay a little bit more to get to 35, so let's try 8,650. A little bit more maybe. And at some point, you see, if we rounded that off, it would be 35. So probably we could quit, but just for funsies, let's keep going. 8675 is pretty good. 35.0 grams per output. So over here, I'd say using TI-83 table X is about 8675. That means the relic is 8,000 years old. That's pretty cool. And this is how they find out how old dinosaur bones and stuff like that is. That's what you saw in the background. All right, that's it for the unit. Lots of homework today, and then review next day, and then the test shortly thereafter.